get into chapter 16, not 6. Oxidation reduction. So we kind of skipped this in the chapter 7 slides because we're going to go into it in depth here. So we did go over the definition of oxidation and reduction, where it's the, we talked about the definition where it was exchanging electrons. Right? Oxidation is loss, reduction is gain. Another way to think about oxidation is the gaining of oxygen. And then reduction being so oxidation, gaining of oxygen. Reduction is the loss of oxygen. Because oxidation, or oxygen, does a lot of oxidation reactions, or takes part in a lot of oxidation reactions. Hence the name. And we did talk about some of these examples as well. So slow oxidation would be like rust or copper corroding also, right? That's why the Statue of Liberty is green. Would have been really cool to see it when it was like bronze or copper or whatever it's made of. And then rapid oxidation, right? Because we talked about combustion reactions. So something burning would be an example of a rapid oxidation. They don't always, redox reactions don't always involve oxygen. So there's one that does, but lithium could also react with chlorine to make lithium chloride. And there's an exchange of electrons going on there. And we'll talk about in a little bit here how we can keep track of where those electrons are going using oxidation states. But again, oxidation is loss, reduction is gain. And you can combine this into a single term, redox, because they always have to occur together. So if something is oxidized, then something else is reduced. Those electrons have to be transferred. So looking at this reaction, we have hydrogen here. Hydrogen in this reaction is oxidized, which makes it the reducing agent. So you can think of this as, if this is oxidized, that means it took its electrons from oxygen. Actually, sorry. It was oxidized, so it was lost. Sorry, it gave its electrons to oxygen, thereby reducing oxygen. And then the reverse is also true. Oxygen here is reduced. Actually, let me highlight these. So hydrogen is oxidized, making it the reducing agent. Whereas, and I know red doesn't show up well, oxygen is reduced, making it the oxidizing agent. So oxygen gained those electrons. And to do that, it had to take them from hydrogen. So it caused hydrogen to be oxidized. So we talked about this acronym, oil rig, or mnemonic, not an acronym. Oxidation is loss, reduction is gain. The implied there being loss of electrons and gain of electrons. So essentially, if you have an oxidation, that's the loss of electrons. If you have an oxidizing agent, that means it's oxidizing something else. It's an agent of oxidation. It's like the Joker was an agent of change. Was that in Batman? So causing change to come about somewhere else. But the oxidizing agent is the substance being reduced, whereas the reducing agent is the substance being oxidized. Oxidizing agent, reducing agent are more terms that we'll use for sort of conceptually. You can really just think of everything as, is it being oxidized? Is it being reduced? And if you can identify that, then you can flip it, and the thing that's being oxidized is the reducing agent, and the thing that's being reduced is the oxidizing agent. So identify first these ones, and then you can figure out the others, what its agent name would be. So I feel like this is putting the cart a little bit before the horse. One of the things that you need to know here is that any free element has an oxidation state of 0. So if we remember, ionic compounds, right, are combined charge-wise so that they balance. So potassium chloride over here, potassium in potassium chloride has a 1 plus charge, and chloride, which is part of the reason that we use that IDE is to designate it as an ion, has a 1 minus charge, but their free element forms don't have any charge. So this is related to oxidation states, but it's not 100% the same. But by knowing this, we can look here and see that if potassium goes from having 0 charge to having a 1 plus charge, then it must have lost 1 electron. And on the flip side, right, that electron has to go somewhere. So for chlorine, we have 0 charge, and we get a 1 minus charge, which means it gained 1 more electron. Oh, this isn't balanced, is it? There shouldn't be a 2 in front of that. Okay, so if potassium is losing 1 electron, is it being oxidized or reduced? Oxidation, yeah, oxidation is loss. So potassium is being oxidized. So then chlorine is being reduced. It won't always be so easy as just 2 elements. Sometimes there'll be more elements. We'll see some examples like that. Here again, though, we can look at these and identify where our electrons are going. So free elements, again, have 0 charge. Their oxidation state is also 0. We'll get to those. So aluminum has a 0 oxidation state. Tin has a 2 plus oxidation state. So sometimes the same as charge, not always. On the right side now, we have 3 plus and 0. Again, because aluminum's charge is 3 plus and tin's charge is 0. So what is our oxidized, or what's being oxidized? Was that aluminum? Yeah, aluminum's being oxidized because it goes from 0 to a 3 plus. So if your charge gets more positive, it's being oxidized because it's losing electrons. If your charge gets more negative, then you are gaining electrons. So tin here goes from 2. Actually, now I remember. We'll use this example again. Think of it as a number line, 0 being in the middle. So if we're starting with tin here is a 2 plus, or plus 2, going from 2 to 0 is moving more negative. So that's reduction. So aluminum's being reduced or oxidized, and tin is being reduced. Yeah, so again, free elements, 0 charges. In molecular compounds, we don't yet have a way for determining what those charges are, or the oxidation states for that matter, right? Because it's not necessarily that they have some charge that we can figure out from the periodic table, combine those together so that those charges balance. So I kind of have to give you here that oxygen here has actually for oxidation states it's -2, and carbon is +4. So each of these oxygens is a -2, and there's 2 of them. So their oxidation states do balance, just like our ionic charges balance in ionic compounds. So what's being oxidized and what's being reduced? Carbon, yeah, going from 0 to +4. I'll do an example over here. Again, using this idea of a number line, we're going from 0 now to +4. So that's Sorry, did I say reduction before? Yeah. Oxidation, though. So this is oxidation. So, and then oxygen is being reduced. Any questions so far? Huh? Not yet. You can feel them coming, though.
Yeah.
That's the same slide. I think I accidentally duplicated a slide. Okay, so in this reaction, again, like that last one we saw with carbon and oxygen forming carbon dioxide, how do we determine what's being oxidized and what's being reduced? Well, I gave you the numbers. Those numbers are the oxidation states. And so that's how we keep track of these electrons. Because it's not always apparent based on charges, like this one with tin and aluminum, very easily giving us those charges. If those charges change, that means that electrons have also changed. These oxidation states we use as bookkeeping for the electrons. The oxidation state or oxidation number is computed for each element based on the number of electrons assigned to it, which partly comes from a table, partly comes from the periodic table. It's not the same as charge, but it will be very similar in a lot of cases. So this is the oxidation number rule chart. How much of that gets cut off? Too much. The oxidation state of an atom in a free element, we covered that one, is 0. So if you have a free element, always 0. If you have a monoatomic ion, then the oxidation state is equal to the charge. For atoms in a neutral molecule, the oxidation states, the sum of all the oxidation states equals 0. If you have an ion, then the sum of all the oxidation states is equal to the charge on the ion. So that's one of the places where the oxidation state is not the same as the charge. All right, so this negative does not apply to all of these. They don't all have a -1 oxidation state. For some compounds, though, they do have consistent oxidation states, just like charges. So our group 1 metals, right, so group 1 is the first column on the periodic table. Those do have the same oxidation state as their charge. They're all +1. For group 2 metals, when they're in a compound, they have an oxidation state of +2. And then I think it's on the next slide. So for metals, you can use these to figure it out. And then in their compounds, for nonmetals, their oxidation states follow this hierarchical table. So essentially, in these cases, the higher on the list it is, the higher priority it has. So fluorine, above everything else, has a -1 oxidation state. So if you have, so then hydrogen has a +1 oxidation state. Oxygen is a -2. Group 7A, so this is where it very much follows the same trends that we've already been looking at, but there's some priority that has to be taken into account. So group 7A, those all have a -1 oxidation state, unless superseded by something like fluorine or hydrogen or oxygen. And then group 6A is a -2 oxidation state, and group 5A is -3. So those are the same as the charges. So to try and illustrate this, if we had a compound of fluorine, let's call it F2, right, difluorine oxide. In this case, fluorine is higher on the list than oxygen. And we know for these non-metal molecules, our oxidation states have to add up to 0. So we start with fluorine, and we say, okay, fluorine in this case, highest priority, has a -1 oxidation state, and there's 2 of those, plus some oxidation state for oxygen has to equal 0. So in this case, because we have a compound of fluorine and oxygen, oxygen here has a +2 oxidation state, which is different from this table. Only because it's combined with fluorine, and fluorine's oxidation state has a higher priority. So for a lot of transition metals, when you're finding the oxidation state, it's like we do with ionic compounds, where you use the non-metal to figure out what the oxidation state on the metal is. And we have other compounds like nitrate. So this is another case of having hierarchy to these charges, or these oxidation states. So nitrogen normally has a -3 oxidation state, but oxygen is higher on the list. So we start with oxygen's oxidation state. Remember, these have to equal 0. So, or actually, sorry. Because this is an ion, this has to equal -1. So for ionic, right, so all the polyatomic ions, it's got to equal the charge for the overall ion. So we have 3 oxygens, which each have a -2 oxidation state. So that's a total of -6. So nitrogen's oxidation state has to get us to -1. So what would that be? +5. Because +5 plus -6 will give us -1. If there was a compound like N2O3-, now we have to take, we would still have 3 times a -2. We still have to equal -1 here, but now we have 2 nitrogens. So each nitrogen is actually going to have half of the charge of our previous compound. So we could, because there's a couple ways that you could look at this. We have 2 nitrogens, so you could think about, well, we need to get 5, a total of +5 here. But we have 2 nitrogens, so you can divide that. I don't know if you can actually have half oxidation states. I'm going to change this to 3. Now that I think about it, I've never seen a half oxidation state. Well, that's not going to help because this is 5. This is why could be why some compounds exist and others don't. Let's make this a 2-. This is what I get for making up molecules. Okay, so still 2 of these. Now that has to equal -2. So each of these nitrogens could be, or would have to be, +2. +2 times 2. So we have 4 plus -6 gives us -2. Okay. So let's assign some oxidation states, a little more practice. For zinc, what's the oxidation state? As a free element. 0. Yeah. For a copper ion with the 2+ charge. The oxidation state for a single ion, whoops, why did I write 5? For the single ion is the same as its charge. Okay, so now we got to do 2 of these. We got to do calcium, and we have to do chlorine. So the oxidation state on calcium chloride will actually determine, There's two ways you can do this, because chlorine is on our list. All right, so for group 7A compounds, it's -1. But calcium also, being a group 2 metal, has an oxidation state of +2. So this compound's not breaking any rules, because we can pull those straight from the table. So there's going to be a +2 for calcium and a -1 for chlorine, which works because there are 2 chlorines. How about for carbon tetrafluoride? Not 0. Well, it has to equal 0. Right, so the sum of these has to equal 0. And in this case, fluorine, remember from this list, is the highest. So if we have a compound of nonmetals, then we have to use that list. So fluorine is going to be 4 times -1. So what is the charge on carbon, or the oxidation state on carbon? +4. So if you're writing out the oxidation state for each atom individually, carbon would be +4, fluorine would be -1. Right, because the oxidation state of each fluorine is -1. All right, for nitrite, kind of like our previous one, we've got a molecule, in this case a polyatomic ion of nitrogen, oxygen, and it has a charge. Yeah, so it has to equal -1? Is that what you're saying? Yes. Yeah, so it has to equal that charge. This is a -1, and then you can fill this in. So we've got 2 oxygens. And again, oxygen is on this hierarchical list with a -2. So each oxygen has a -2. And the nitrogen then has to have the charge that's going to get us to a -1. So if these together are +4, this has to be a -5. So nitrogen will be -5. Oxygen will be -2. Because again, we're writing down what each oxygen is. So if we have our last one here, SO3. Notice again, there's no charge on this one. So this will be equal to 0. And then we'll have 3 oxygens. And again, oxygen is higher on the list because it's fluorine, hydrogen, oxygen, and then everything else. So we'll just do -2 for oxygen, for a total of -6. So sulfur's oxidation state, +6. So we'd say sulfur has a +6, oxygen has a -2. Any questions?
So for E, wouldn't it actually be where n is -3 because -2 times 2 is -4?
Oops. Wait, hold on. Yeah. Because this is -4. This is +3. Yeah, I goofed that math up. Yes. Any other mistakes that I made? That's good. It's good. I've made a lot fewer mistakes this semester already than I have in past ones. Any other questions, though? Okay, so now we can come back to this problem and take another look at it. So if we have, right, this is a free element carbon, free element sulfur. Both of these have oxidation states of 0. Our oxidation state on carbon now we know we can figure out from the oxidation state of sulfur. So we'll probably run out of space doing this every time. But after fluorine, hydrogen, and oxygen on that list, then we just move right to left from group 7A to 6A to 5A. So 6A is sulfur, so same as oxygen, has a -2 oxidation state. So carbon, so this is a -4. This has to equal 0. So carbon must be +4. So now we can also look at these and say, okay, if carbon is a +4, each sulfur is a -2, we can see that carbon went from 0 to +4. So if we want to number line this, think about 0 going to +4. That's, you have to lose electrons to move in that direction. Oxidation is loss. So carbon was oxidized. Sulfur went from 0 to -2. Reduction is gain. So sulfur was reduced. What do you think? Yeah. Increase or decrease in oxidation state? Oh boy, oh boy. So now using this in an actual chemical reaction, I think the easiest place to start is identify if you have any free elements. So tin, free element, is 0. Some of these, if you get good enough at this, you'll notice that something like nitrate is always going to have the same oxidation states. And furthermore, some things like hydrogen and oxygen, unless they're paired with fluorine, are always going to have the same oxidation states. So you can pretty quickly go through here, recognize that hydrogen is going to be +1. Nitrogen, well, let's do this for right, because this is nitrate. So if this has to equal a -1, we have 3 oxygens, which are all -2. So again, that's -6. So nitrogen must be a +5. So nitrogen is +5, oxygen is -2. What's the oxidation state on tin oxide? On tin in tin oxide? The oxygens are all -2. There's 2 of them. Then the oxidation state on tin has to be 4. All right, so if we wanted to do this like this again, all right, so this has to equal 0 because there's no charge on the ionic compound in this case. Oxygen, we have 2 of those, each at a -2. So that's -4. So tin has to be +4. So +4 for tin. And again, here, each of the oxygens is -2. Because we're tracking these we're tracking the electrons for each atom. Then in nitrate, we can kind of draw a parallel here between tin, or sorry, not nitrogen, but nitrogen dioxide, because it's something paired with 2 oxygens. So if we have nitrogen here with 2 oxygens, what's the oxidation state on nitrogen? +4 again. And then each oxygen is still -2. And then hydrogen, is always going to be +1, and oxygen will always be -2. Okay. So now what is being oxidized? What is being reduced? Let's start with what's being oxidized. So if you compare atom to atom from the left side to the right side, starting with tin, we find that it goes from 0 to +4. So that's a change in oxidation state. So we know that's either being oxidized or reduced. And since we're going from 0 to +4, it's being oxidized. Yeah, it's oxidation. This is being oxidized. If we keep going, we can look at hydrogen, say that hydrogen here is a +1. Hydrogen over here is also +1. So that hasn't changed. Nitrogen, whoops, all right. Did I undo more than I wanted to? No, we're good. Okay. So nitrogen here is a +5 on the reactant side, but on the product side, it's +4. It's been reduced, yeah. And again, we can use a timeline or number line to help identify that. So we've actually gone from +5 down to +4. So that's moving to the left. It's lowering the oxidation state. So it's being reduced. And then if we look at oxygen, we can see that on the reactant side, it's -2, and everywhere it exists on the product side, it's still -2. So oxidation state hasn't changed. It has not been oxidized or reduced.
Should we label it as anything, or would we just leave it blank?
Just leave it blank. This kind of question will probably be like this. I'll give you a reaction, probably balanced, and say it'll be multiple choice. Right? So I'll give you tin, nitrogen, hydrogen, oxygen. Say, which of these is being reduced? You'll just circle one. And there might be a follow-up question, which is being oxidized. Yeah. Any other questions? This oxidation, reduction, redox reactions is kind of a lot, I know. Okay. So redox reactions occur in aqueous solutions, are difficult to balance by inspection. So that means looking at the atoms and deciding how many more of each thing that we need, because the electrons are largely invisible in terms of a chemical reaction. Right? Looking at this reaction up front, it would be very difficult to try and balance without setting the oxidation states. So what we do instead is something that's called the half reaction method. You will see other versions done out there. If you go and you find those on YouTube or something, if you're at Khan Academy, actually I've mentioned Khan Academy a few times, but it's Khan Academy. Did I spell academy right? Doesn't look right. Okay. Spelling was never my strong suit. So if you go and you find the other version and you like that better, then by all means do that. But we're going to learn the half reaction method. So you identify the oxidation and the reduction in the reaction, and you break those apart. And so we'll balance the oxidation and the reduction separately. And then we can add those equations back together. So based on this redox reaction, you can go through and assign oxidation numbers. Again, we can find our free elements and know that those are 0. And then for individual ions, their oxidation number is the same as their charge. So we can identify which is being oxidized and which is being reduced. So aluminum going from 0 to +3, that's being oxidized. So that's half reaction would be aluminum solid as our reactant, and then our product there would be aluminum 3 plus as the product. Our other half reaction would be silver reacting to make silver solid. All right, so once we have those separate half reactions, we move on to the next step. Oh, I didn't erase this. There we go. So these half reactions, you balance first with regard to mass. So look at both sides and make sure that we have the same number of atoms. So like we would balance any other equation. In these ones, 1 aluminum, so we're good. The other thing that we do is we balance by charge. So we look at either side and we say, okay, the left here has a 0 charge. The right side is 3 plus. And we add electrons to make them the same. So in this case, we can only subtract 1 at a time. So on the right, we have 3 plus. So we can subtract 3 by adding 3 electrons. So each electron adds a 1 minus charge for an overall charge of 3 minus. So that 0 equals 3 plus 3 minus, which would be 0. For our reduction reaction, we do the same thing, except now we have 0 charge over here, 1 plus. So we add in just 1 electron, which is a 1 minus. So that 1 plus 1 minus equals 0. Then once you've gotten to this step, we need to make the number of electrons in each half reaction the same. So we can do that similar to when we get fractions in balancing. We just multiply the entire thing by a coefficient, or multiply all the coefficients by the same number. So because we have 1 electron in our reduction reaction, and we have 3 electrons in our oxidation reaction, half reaction, we multiply the reduction reaction by 3. I'm going to rewrite this. So we'll get 3 Ag plus 3 E minus 3 Ag solid. So didn't do anything to change the balance of this, right? We still have the same amount of atoms on each side. But even just thinking about this as, if this aluminum is going to lose 3 electrons, those 3 electrons have to go somewhere. And in this reaction, we have silver is only gaining 1 electron. So we need 3 silver atoms to gain those 3 electrons from aluminum so that our final reaction is balanced. Didn't erase this one either. So the final step here, once we have these 2 reactions and we've balanced in each of them the mass, the number of atoms, and we've balanced the charges, and we've made sure that each of them has the same number of electrons, we can add those together. So if you want, you can write a line like this, and we're going to do 3. And again, the order here doesn't matter all that much. Plus aluminum solid plus 3 electrons. And then our other side of the equation is going to be, Ag solid plus Al3 plus 3 electrons. So then kind of like our going from the complete ionic equation to the net ionic equation, we have these 3 electrons that are the same on both sides. So we can actually remove those from our final reaction, because those have been taken into account in the actual numbers of atoms that are present. So your final check is, are the charges on either side the same? So this is 3 times the 1 plus charge of silver. And then so that's a 3 plus on that side. On the right side, we have the 1 aluminum 3 plus. So total charge there of 3 plus. Any questions so far? These are, again, problems that you should go back and try. We got a whole set of them that we're going to do, but go back and try these without any notes, without looking at anything else. Start from a blank slate. So the procedure then overall is assign oxidation states, separate the overall reaction into 2 half reactions, right? Oxidation, reduction reactions. Balance all elements other than hydrogen and oxygen. Then, if you have to balance hydrogen or oxygen, you balance oxygen first by adding water to one side. And then you balance hydrogen by adding H plus to one side. And I crossed out this last one because we're not going to worry about whether it's acidic or basic. Leave that up for a minute. Good. So once you've got hydrogen and oxygen balance, then you balance each half reaction with respect to charge by adding electrons. You make the number of electrons in both half reactions the same by multiplying the entire thing. And sometimes you have to multiply both half reactions by some coefficient. So they have the same number of electrons. Then you can add them together, cancel anything out that's the same on both sides, and then verify that the reaction is balanced by counting. You can count atoms, and you can also count the charges. Make sure that the charge and number of atoms on either side is the same. Okay. So another reaction to balance. Our first step is to identify the oxidation states. So for ions that are by themselves, it's the same as their charge, +1. Chromium here is a free element, so it's 0. Hydrogen, H2, is also a free element, 0. And then the oxidation state of the chromium 3 plus is +3. So once we've identified that, we can separate this into the 2 separate equations. You don't necessarily need to know which one's oxidation and which one's reduction, but that can help you identify which, in more complicated reactions, which ones to actually separate into what equations. So here we have hydrogen gaining 1 electron to make it neutral. So that's our reduction reaction. So it's going to be our H plus, aqueous, and then H2 gas. And then chromium here going from a 0 to a +3 is losing 3 electrons. So that's a oxidation. So chromium solid goes to chromium 3 plus, aqueous. Okay, so step 1 complete. Or actually, I think that's step 2. So our next step is to balance, if necessary, any oxygens first. Don't have any oxygens at all, don't need to balance those. Next, we balance hydrogens by adding H+. So for this top reaction, we actually need to add another hydrogen. And because we already have an H+, we're just going to change its coefficient to 2. Because we had one H+, we're adding one more. So 2 H+ ions there total. And then with regard to mass, chromium's already balanced. So now, having balanced that, we can go through and balance the charges on either side by using electrons. And again, the charges have to be the same. So on this one, we have a 2+ on our reactant side for the hydrogen reaction. And on the product side is going to be a 0 charge. So which side and how many electrons do we need to add? Two electrons on which side? Yeah. Oh, no. On the other side. So remember, everyone's a 1- charge. So you write 2 electrons over here, because we'll get a 2-. It is definitely a mistake that I made a lot. It's like, oh yeah, add them on the right side, because then I've got 2 and 2. But you're subtracting 2, or you're subtracting 1. You can only make it more negative. All right, for our next reaction, which side and how many? Electrons. Right, so if this is 0, this is 3+.
3 electrons on the right.
On the product side, yeah. Plus 3 E-. Okay. So now we've got those balanced, or we got the right number of electrons for each of them separately. We need to make the number of electrons the same for both of them. So this is, we have 2 electrons here and 3 electrons here. So we've done something like this. This comes up a lot. But it's kind of like the crisscross rule. So this one has 2 electrons. This one has 3. We have to multiply the top one by 3, multiply the bottom one by 2. Can I give myself, showing myself a little more room here. So then the top reaction will be, the hydrogen reaction here will be 6 E- plus 6 H+ and 3 H2. And then our chromium reaction will be 2 Cr, so 2 chromiums, 2 Cr3+ plus 6 E-. And the final step is just add those reactions together. And because we have 6 electrons here, 6 electrons on the other side, yeah, they cancel out. So we're just left with 6 H+ plus 2 Cr solid, 3 H2 plus 2 Cr3+. So again, remembering here what's going on with the redox reaction is we're exchanging some number of electrons. And after balancing it, that's this number of electrons. There's 6 electrons that are being exchanged for every cycle of this reaction. So we got chromium here, right, losing 6 electrons. Well, each chromium losing 3, but times 2. And then the hydrogens, there's 6 hydrogens, gaining all of those electrons to form 3 H2s. So we can check our balance here by looking at the charges. So this is a 6 plus and 6 hydrogens, each one with a +1. And then we also have 6 plus because we have 2 chromiums, each with a 3 plus. Any questions? Still good? Alrighty. We got, I think, several, three more examples that we'll do, and then we'll hopefully we can get through those fast enough, and then we can do activity series very briefly. So balance a redox reaction occurring in nitric acid, in an acidic aqueous solution. Here we've stepped up the difficulty for calculating oxidation numbers a little bit. But we can still go through and identify free elements as 0. Those are always gimmies. And then any free ions as their charge. So copper over here will be a +2. Then for nitrate and nitrogen dioxide, we'll use oxygen to determine what the oxidation state on nitrogen is. So you can do that if you want by writing out that equation. So this is NO3 minus. The overall charge has to be the same as the oxidation state. So if we need this to be a -1, the one we know is oxygen. So it's 3 times a -2. So that'll give us -6. So nitrogen is +5. So nitrogen here is +5. Oxygen is -2. Again, always writing down the oxidation state for a single oxygen. Then for nitrogen dioxide, if oxygens are always -2, then 2 oxygens at -2 is -4. So our oxidation state on nitrogen has to be +4. Okay. Now this is one where you don't necessarily need to write out the oxidation states to probably identify which half reactions we're going to pull apart. Because we have one instance of copper as a reactant and one instance of copper as a product. So it's going to be one of them. But for the sake of going over these things over and over and over again, copper here with a 0 ends up with a +2. So oxidation is lost. So we've oxidized copper. That'll be one of our reactions. So copper solid going to copper 2+. And then our other reaction will be nitrogen, and we're going from a +5 to a +4, and it's being reduced. It's gained 1 electron. So this will be NO3 minus going to NO2 gas. So our next step then is to look at these and balance based on mass. So we've got the same number of coppers, we've got the same number of nitrogens, but we need to balance the number of oxygens. And so we do that by adding water. It's an aqueous reaction, so you can really just add water in to make that balance. So we'll get NO3 has 3 oxygens, NO2 has 2 oxygens. So if we need one more, we just say add an H2O. But that, of course, has changed the balance of hydrogen, because we didn't have any before. So this is why you balance oxygen before you balance hydrogen, because now we can add H plus to balance those hydrogens. So we're going to add 2 H plus. And then once we've balanced all of our atoms, we can balance the charge by adding electrons. So again, for a copper reaction, it's 0 on the reactant side and a +2 on the copper 2+ side. So which side and how many electrons do we add? 2 electrons to the products. That is correct. Because then we'll get a -2, +2 plus -2 is 0. So we've satisfied that one. Here in our nitrogen, in our reduction reaction, we do have to take into account the fact that nitrate has a 1- charge already, and then we have these hydrogens, which each have a +1. So if the overall charge here is +2, and this is -1, that has to equal what's on the other side, which is currently 0. So our overall charge on our reactant side will be +1. So if we've got +1 here, then we need to add 1 electron over here as well. Sorry, I should do it like this. Right, that overall is +1, but if we add this, another minus there, now both sides are 0. Yeah, we're going to run out of time. That's okay. Yeah, okay, that's fine. So then our copper reaction has, or our last step here I should say, is that we go to balance the electrons. So we balanced electron or charges on each of the half reactions, but now before we combine them, they have to have the same number of electrons in each reaction. So for this half reaction, we have 2 electrons, but for this half reaction, we only have 1. So we need to go through and multiply this whole thing by 2. So every coefficient gets multiplied by 2, so we'll have 2E minus plus 4 H plus 2 NO3 minus 2 NO2 2 H2O. So we take these 2 reactions, because I'm going to run out of space otherwise, and add those together. And again, since we have the same number of electrons on both sides, those cancel out. So the final reaction should be 2NO3 minus, it's not equals, and then the last step, we can check the charges. So 4 hydrogens, this is +4, but this is -2. And this is 0, 0, 0 charge, +2. So it does balance. We have +2 on both sides. All good so far? Okay. Keep on trucking. Is there? Okay. So again, first step, identifying oxidation states. What's the oxidation state on tin? 0. Free elements. Gotta love them. What's the oxidation state on manganese? Not 0. positive 1. But we have 4 oxygens. So that's negative 8. But it needs to equal minus 1. So we've got negative 8. This is positive 7.
The rules are listed right on a couple pages back, right?
Yeah. Ooh, that's a good question. Yeah, I think I will put those on there. I think I will put those. I'll put the rules on there. Yeah, I'll put the rules on there. Yeah, that would take up a lot of space on the cheat sheet. I'm going to end up putting everything on there. Okay. So we've got all of our oxidation states. Again, for these ions, stays the same. Or it's the same as the charge. So tin's going from 0 to positive 2. Is that oxidation or reduction? Oxidation, yeah. So that'll be one of our reactions. Tin to tin ion. That makes our other reaction, reduction. O4 minus. Oops. Okay. So what's our next step? What do we balance next? Could be our electrons, could be oxygens, could be hydrogens. Oxygens, yeah, for the manganese reaction. So we add waters. So you add as many waters as you need oxygens. So in this case, we need 4, so we had 4. 4 H2O.
So you would balance it out with water, or you would add water in what case, you said?
If you need to balance oxygens.
If you don't have any on the other side.
Right. Right, yeah, because those oxygens have to go somewhere, so they become water. Yeah. 8 waters. Yeah. And now, because we added all those oxygens, we've added hydrogen also. So now we add 8 H pluses on the other side. And the reason we can just pull these out of the air is because they're actually there in the solution. They just haven't been identified here. They haven't been tracked there. Because this is all taking place in an aqueous solution. So it's all dissolved in water anyway. Okay, good. What do we balance next? The 3 options were hydrogens, oxygens, and electrons. So we do the electrons. For tin, again, the way we balance the electrons is by making the charge the same on either side. Not necessarily 0 all the time. I think we saw that actually on the last example. But just the same. And you can only subtract. Yeah, so 2 electrons on the product side. Gets just slightly more tricky when you add other ions. This is going to be positive 8. And we have a minus 1. So overall of positive 7. And maybe I could write that here. We could say this is overall on the left, positive 7. And that needs to equal, on the right side, just a positive 2. And we can only subtract. So which side are we subtracting from? The reactants. Yep. So like I was just saying, it doesn't have to be 0 on both sides, just has to be the same. So we add 5 electrons, because now we'll get minus 5. Change slides. So then this will be an overall charge of plus 2. So charge is balanced on either side. What's the last step before we add them together? Multiply, but what? And by what? We need the electrons the same. Yeah.
So it'd be 3? No.
Yeah, you basically do cross multiply, so that same sort of idea.
Yeah.
So if this has 5 electrons and this has 2, then we need to multiply this top one by 5, the bottom one by 2. Let's see if I can squeak this in here. 5, 10, 5, 10, 2 plus 10 electrons. And this one's multiplied by 2, so we're going to get 10 electrons, 16 hydrogens. Whoops. And now we can add them together. I will say that there will probably not be too many, probably be like one redox reaction that you would have to balance because these take a long time. There will be questions like, what is the oxidation state on this atom? What is the oxidation state on that atom? That kind of thing, right? Those are pretty quick and easy to identify, but doing this whole thing takes a minute. So we can add these together. Electrons are the same in both, so those cancel out. And we'll get 16H plus. Cool. Any questions on that one? I think this is about as complicated as the oxidation redox reactions that I would give you. This next one's a little more complicated and also involves a basic solution, so we're just going to skip over that because I do want to get through activity series. But if you want to try this problem on your own time, by all means, send it to me if you have questions. The activity series is really, and this is the kind of thing where I would give you the activity series on the exam and you would be able to use it because it's identifying if a reaction is going to be spontaneous, a redox reaction in particular, based on the series. So if we place a magnesium strip in a copper solution, it'll be oxidized. We've got magnesium metal going into copper ions. But if you place a copper strip in a magnesium solution, magnesium ion solution, nothing happens. So what's going on is there's sort of the copper wants the electrons more than the magnesium. And so the copper is able to steal the electrons away from magnesium. So in this case, right, we have copper gaining those electrons, so being reduced, and the magnesium's being oxidized. So if you try to do the opposite, though, the copper still wants those electrons more than magnesium, and the magnesium doesn't have enough power to take them away. So you can think of, sorry, I just had funny thought, because this is the activity series. You can think about this as like a tier list of metals, and which metal is going to beat another metal in a fight and steal its electrons. We'll go back to this real quick. So this activity series is this tier list of which metals have the greatest tendency to lose electrons. It's kind of like an upside-down tier list. They're the ones that are the weakest, right? So they will give up their electrons the most easily. Metals at the bottom of the list have the lowest tendency to lose their electrons. So they lose the fewest fights. So if you have half reactions, so these are all half reactions. So if you're to compare any two metals here, the metal that's closer to the bottom of the list, let me just double check and make sure I'm saying this correctly. Half reactions at the top of the list are most likely to occur in the forward direction. So looking at lithium, lithium is losing an electron. So it's more likely to lose that electron. half reactions at the bottom of the list, gold here, for example, it's more likely to happen in the reverse direction. So it's going to gain those electrons. So if you had gold ions in a lithium, or if you put a lithium metal strip into a gold solution, gold would beat up lithium and steal all of its electrons in a hurry. So any ion on this list that's lower is going to react spontaneously with anything that's higher on the list. So gold will beat silver, silver will beat copper, silver will beat, right, any of these up here. So that's how you can use this activity series. And this also explains why gold is very hard to oxidize. It doesn't react with anything because it beats everything else up. Sorry, I really like that analogy. That's why things like silver and gold, right? Silver also, which silver does corrode a little bit, gets a nice patina, but generally reacts very little. So those are the precious metals. Very quickly, I know it's 6:23, but if we have zinc, so we've got zinc in the activity series with a nickel solution. So zinc is here, nickel is here. Is this reaction going to be spontaneous or not? So it's the nickel, right? So this will be a nickel 2+ ion, and the zinc 2+ ion. Nickel's lower on the series. Yeah, so nickel will take those electrons from zinc, so this will be a spontaneous reaction. If we have zinc and calcium, so we've got zinc, metal, and then we have calcium ions. So that zinc ion, yeah, is not strong enough to steal the electrons. Or sorry, the calcium ion's not strong enough to steal the zinc, electrons from zinc. So this would be non-spontaneous. And that's sort of the extent of what we'll use the activity series for. So you'd be given that. The one last thing you can do with the activity series is determine if it'll dissolve in hydrogen. Or if if an acid will dissolve a metal. So metals above hydrogen on the activity series dissolve in acids, same kind of thing, while metals below hydrogen do not dissolve in acids. So here's hydrogen on the activity series. If silver is below hydrogen on the activity series, will it dissolve in acid? No. Only if it's above. Right, metals above dissolve. So if you want to dissolve silver or gold, you have to use something called aqua regia, which is a combination of sulfuric acid, nitric acid, and I think hydrochloric acid maybe. Super, super nasty stuff. All right, that is chapter 16.